Alrighty, we're recording. Yep. Okay. So, get the markers. So last time we talked about Newton's laws, okay? Oh, this marker is not that good. It's okay. And I talked about Newton's second law and the third law. And we discussed examples relating to this. And one of those examples I haven't given you a lot of problems about was the elevator problem. So I told you sometimes if you have people in an elevator like this, is that okay? So sometimes the elevator might be accelerating up or moving at constant speed up or moving down at constant speed, or it might be accelerating down. Is that okay? So in which case, if we say it's going up with an acceleration of say 100 meters per second squared, that's pretty fast, but just in case, okay, you see this first. So I can ask you if the tension in the string holding the elevator T is say 10,000 newtons, I can say what is the weight of the people in there. Is that okay? So one way to get that is you say T, since it's going up, T is bigger than the weight, T minus weight equals MA. Is that okay?
Why is T greater than the weight?
Because it's going up, it's accelerating up. So the tension is going up. Is that okay?
Yeah, because it's actually moving.
It's moving up, accelerating. So T minus the weight equals MA. And weight is mg, so T minus mg equals ma. Is that okay? So I can get mg plus ma equals T. So m into g plus a is T. So I know G 9.8. I usually use 10 in this class just to make easy calculation. And I'm giving A equals T. So my mass is T divided by G plus A. Is that okay? So that's the mass of the people in that. So that's going to be 10,000 divided by, say, 110, if I'm taking G to be 10. So 100 meters per second squared plus 10. So that gives me the mass. So getting that mass, I have to multiply by G to get the weight. So if it's accelerating down, it's the opposite. So it will be weight minus T equals MA. Is that okay? So because the weight is now greater, that is producing the acceleration. And then if it's moving at constant speed, then weight minus T or T minus weight is 0, so they are the same. And that is when you measure the same weight you have in the elevator. So if the elevator is accelerating up, if I have a scale, a weighing scale on an elevator, I stand on an elevator, the elevator is going up, accelerating, I will measure a higher weight. If it's going down, I'll measure a lesser weight. If it's going down, accelerating down. But if it's moving at constant speed, whether up or down, I'll measure it at my exact weight.
Is that why when you get in the elevator and it starts,
it's like put some force, yeah. So it puts some force on you, yeah. Yeah.
And then afterwards it's normal.
Yeah, it's normal.
Speed.
Exactly. So most elevators usually move at constant speed just to make you feel normal without accelerating. But those, I think those that have very high, like the floors, some of them accelerate for a while just to take you faster before they slow down.
I was in one in New York and it accelerated for a while.
Oh, okay. Okay, yeah, New York have these tall buildings. I was in LA too, and they had all these big hotels with these tall buildings. You go to like 50-something floor, be like, what?
You can use it. You go fast.
Yeah. Okay. So, like I said, our next class, we're going to do just problem solving from chapter 1 till this chapter, just to review so that we can do more on this. Now, we're going to use this Newton's laws to apply, for today, we'll apply Newton's laws to circular motion. So I'll introduce you to circular motion today, okay? And see how Newton's laws work in circular motion. Is that okay? Okay, so So circular motion is quite different from rotational motion. Rotational motion is going to be another topic we'll treat very soon. Is that okay?
I'm sorry. Oh, rotational.
Rotational motion is different from circular motion. So we are doing circular motion. We are not doing rotational motion yet, but we'll come to this. And we're going to see how they are related. Okay, they are quite related, both of them. Okay. So when you move in a circle, you move about a point outside you. So you are here. Is that okay? And there is a circle here, like a bathtub, and you are going around this bathtub. So this is the center of your circle R, okay? So you are going around this bathtub. You are going in a circle. You are not rotating. Is that okay? When you are rotating, it means you are going around yourself. So the center of the circle is yourself. So a point about you like this, you are rotating. Is that okay? Good. So rotational motion, when we discuss it, we'll discover rotational motion has circular motion inside it. Is that okay? Because when I have the fan blades rotating, is that okay? The tip of the fan is going in circular motion. So every particular point I consider is in circular motion. Is that okay? But a point moving in circular motion, that is what we're discussing right now. We're not looking at rotation. We'll come to rotations, we discuss moment of inertia and some other properties of angular momentum conservation and things like that. Okay? Okay, now, talking about circular motion, we need to define certain things first, okay? Some of you always hear of 2 pi radians is 180 degrees, right? And you just memorize that, right? So 2 pi radians is 360 degrees, sorry. And then pi radians is 180 degrees. Is that okay? So we're going to define some of these things. Is that okay? And tell you why this is that. It's not something you just memorize. It actually has some basics included inside of it, okay? All right. So now, to start my circular motion, the first thing I want to talk about is to consider a circle, an object going in a circle. So I know there is a radius r, right? What line is this? It's still a radius. I'm just confused.
Oh, okay.
So anyway,
like, radius?
yeah.
No.
What about this one? Okay, good. I'm just trying to see if you're awake. Yeah? So radius, any line from the center to the circumference is a radius, right? So what happens is, if I have an object move from A to B, so this distance in this arc, is that okay? The distance covered along the arc, I call it S. So arc length, I call S. Is that okay? That distance from A to B is actually the magnitude of a displacement. So I call it linear displacement. Linear what? Displacement from A to B. Is that okay? So you are going around a circle, but I can take this part of the circle out and stretch it out and say you just move the linear distance. Is that okay? Is that okay? From A to B. Another way to describe the linear displacement from A to B is to say, instead of giving you the arc length from A to B, I'll just give you the angle theta you move. So you move from A to B, this angle theta. If I give you that angle theta is what we call the angular displacement. Angular displacement. So linear displacement is the normal displacement we know. It is measured in meters. Angular displacement has the SI unit of radians. Don't get this confused. It's the same angle you know before that is measured in degrees. Degrees is another unit. Just like you have miles and meters and inches and feet. Different units of length. But the SI unit is meters. So we have degrees, revolutions, cycles, rotations, radians. These are the same unit of angular displacement, but the SI unit is radians. So what is the radians? Okay? What is radians? Okay, now, let me put this check here so I have space to exercise myself. So if I have a circle like this, is that okay? And a particle starts from point A, the radius of this circle is R. If I move from A to B, a distance S equal to R. When I move an arc distance that is equal to the radius of my circle, then the angle subtended is said to be 1 radian. This is the definition of a radian. Is that okay? So when you move an arc distance equal in magnitude to the radius of your circle, then you have moved an angular displacement of 1 radian. That is why radian is very small compared to degrees. Pi, the pi in radian is the same pi we know, 3.142. Pi radians, 3.142 radians is just 180 degrees. Is that okay? Is that okay? That's why radians is small. Now, from this understanding of what the angular displacement is and the definition of the radian, is that okay? Now we'll proceed to see some more important things. Is that okay? Nice. Okay, we're going to draw a lot of circles today. Plenty circles, okay? You're good. You're good. Just do like this. It's a circle. Now, I have radius R, right? So I go from A to B. Is that okay? So let's say I go a distance R. Is that okay, from A to B? And I know my theta. So if I say AB over theta, I'm taking a ratio. AB divided by theta. The ratio I'm taking is 2 pi R. So AB, the arc length, divided by the angle. I'm taking another arc length, the whole circumference, divided by 360 degrees. Is that okay? So I'm doing this side and this side as 2 different ratios, but they are the same. So any arc length I take divided by the angle is the same if I take another arc length divided by the angle, right? So if I'm working in radians, on my left-hand side, then I know AB is R when theta is 1 radian. Is that not? And this is 2 pi R over 360 degrees. So my right-hand side is in degrees, my left-hand side is in radians. Is that okay? So when I cross-multiply to see the conversion, R cancels R, 360 degrees is 2 pi radians. Is that okay now? 360 degrees becomes 2 pi radians. And if you divide by 2, you get that pi radians is 180 degrees. Is that okay? Is that okay? Good. So this is the same as 1 cycle or 1 revolution. Is that okay? Or 1 rotation, if you like. Is that okay? These are different units. Is that okay? But the same thing. And when you have a problem, most of the time, when you have a problem in this structure, when you're doing circular motion, you have a problem like this, you have to convert from revolutions to radians. Is that okay? For the most part, before you work in SI unit. Okay. Are we good to go to the next step now? Alrighty, so let's go to the next step. Please feel free to ask questions anytime, okay? Okay. The next step now. The next step now is to define some other things. Okay, so I have the circle again. I have my AB. Now I'm going to work all in radians. Is that okay? So AB theta, AB is not R now, but AB is just any AB. Theta is any theta, but this all in radians. Is that okay? So this is equals. Is that okay? This is equals. I say 2 pi R divided by 360 degrees is just 2 pi radians. Is that okay? I'm working everything in radians. Is that okay? So any AB, S, over any theta in radians is 2 pi R over 2 pi. So 2 pi cancels 2 pi. I get S is R theta. I call this equation 1. That equation is relating linear displacement to angular displacement. It's telling me linear displacement is radius times angular displacement. Is that okay? Now, I'm going to divide equation 1 by time. Is that okay? I'm going to divide equation 1 by time. Okay? If I divide equation 1 by time, I get S equals R theta divided by time. So I get S over time on the left-hand side equals R times theta over time on the right-hand side. S over time is linear displacement divided by time. That's linear velocity V equals R times theta divided by time is angular displacement divided by time. That's angular velocity omega. Angular velocity omega. So I say V equals R times omega. V is linear velocity in meters per second. Linear velocity measured in meters per second. And omega is angular velocity. Angular velocity measured in radians per second. Is that okay? So meters per second is radius times radians per second. Is that okay? Is that okay? So S is R theta, V is R omega. So I call this equation 2. You can guess what's going to happen next, because I'm going to divide equation 2 by time again. And what do I get? I'll get V equals R omega, V over time, R omega over time, V over time equals R dot omega over time. V over time is linear velocity divided by time, linear acceleration A. R times omega divided by time is angular velocity divided by time, angular acceleration, alpha. So I say linear acceleration measured in meters per second square equals R times angular acceleration. Angular acceleration measured in radians per second square. Is that okay? Is that okay? Is that okay? Okay, so this is equation 3. Equation 3. Now I want to tell you how all these things we've defined. Linear displacement, angular displacement, linear velocity, angular velocity, linear acceleration, angular acceleration. How they act in a circle. Is that okay? How they act in a circle. Okay, how do these things act in a circle? Okay. Now, if I have a circle, so the first thing is at this point I'm moving with some omega along the circle and some alpha along the circle, maybe. Is that okay? But the point is, the linear parts are not like along the circle. The linear parts are not along the circle. The linear parts are tangential. Is that okay? So my omega and alpha along the circle, but my linear V and alpha are tangential to the circle at every point. So that is why, even if I don't have alpha, say I'm moving at a constant angular velocity, only omega, I don't have acceleration along the circle, the angular velocity can be constant, but your linear velocity is never constant because your direction keeps changing. Every point you have different tangent. Every point you have different tangent. For the tangential velocity, we'll call it V tangential. Is that okay? So it is this V tangential that is R omega. Is that okay? Is that okay? It is that V tangential at every point that is R omega. So the velocity, the linear velocity, the tangential velocity is never constant. But your angular velocity can be constant. Is that okay? Your angular velocity can be constant. And when we come to rotational motion, we'll explain more about this because this is important. Because if I have a disk that is rotating, so a disk is a solid thing like this, so it has some thickness and it's rotating. So because V is R omega, so even if this disk is rotating at a constant omega, a point A here and a point B here will not have the same velocity because V is radius dependent on omega. So those that have the short radius will have small velocity. Those that have the larger R from the center will have larger tangential velocity at that point. But we'll understand more about that when we do rotational motion. Is that okay? Yes. 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 So the velocity is never constant. But the angular velocity can be constant. Is that okay? Now let's look at the case where we have a constant angular velocity. Angular velocity. Okay. So if I have a constant angular velocity omega, it means I don't have no alpha, I don't have any angular acceleration, but I have a tangential velocity that is not constant. Is that okay? But the thing is, even if I don't have an angular acceleration, I'm moving at a constant angular velocity, it's just like a fan rotating steadily, I still have some linear acceleration called the centripetal acceleration or the center-seeking acceleration. I call A subscript C. So the centripetal acceleration is the acceleration that is always acting towards the center of the circle. It doesn't care where I am. It's always towards the center of the circle. AC, AC, AC. So irrespective of me moving with a constant angular velocity, I have this centripetal acceleration that tries to drag me into the center of the circle. Is that okay? So when I'm whirling a stone in a circle, a horizontal circle around my head, or a vertical circle like this, or what you call a conical pendulum, we're going to see all these cases. When I do that, I can always feel the force dragging the stone to stay in the center and stay in the circle. That is the centripetal force. So centripetal acceleration is V square over R. But V is omega R. So it's omega R square over R. So it has another formula of centripetal acceleration is V squared over R. R cancel one of the square, omega square R. Centripetal acceleration. And this centripetal acceleration furnishes what we call the centripetal force. The centripetal force is always dragging objects to the center of a circle. And this centripetal force is just mass times the centripetal acceleration. So centripetal force is mass times centripetal acceleration. So it's mv squared over r, m omega square r. Is that okay? Is that okay?
So that's mass times the acceleration.
Exactly. So mass times this. Yes. Is that okay? Centripetal force. So this is what we call centripetal force. Yes, so we good?
I actually have a little ball on a string.
Uh-huh.
If you wanted to demonstrate that.
That's okay. It's okay. It's okay. We all know how this happens. Is that okay? Is that okay?
Yep.
Okay. Now, let's look at the case where I have alpha. Now, I turn the fan on. It starts from rest. So it starts from omega equals 0. And then it starts moving, accelerating with some alpha. Is that okay? It starts accelerating with some alpha. Is that okay? So what happens is, in this case, I'm going to have two accelerations now. The first one is the centripetal acceleration. The second one will be the tangential one as a result from this alpha. Is that okay? So we have an A tangential and an A centripetal. So we are going to have these two accelerations when I have an angular acceleration. And then we're going to have a net acceleration. A net. So A net is square root of A centripetal square plus A tangential square. Is that okay? That's a direction given by theta all the time. Okay, A centripetal square plus A tangential square. Square root give us A net using our vector notation for vectors acting orthogonally, right? Okay. So, when I don't have alpha, I still have centripetal, but I don't have tangential acceleration. Is that okay? But when I have alpha, centripetal and tangential combine together. Is that okay? And when I have alpha, it becomes a non-uniform circular motion. And for non-uniform circular motion, we have the exact same kinematic equations as we have for linear motion by substituting every linear quantity with angular quantities. You see what I'm talking about right now in a jiffy. I'm going to write that one down here. I'll do that one down here. Okay. Like I said, examples here are really simple. So I can just give you mass and say find centripetal force, or give you the force, say find the mass. You know, just simple things like that. We'll come to complicated ones, okay? So now, for my kinematic equations, I have my linear equations. Now I will give you the angular equations or circular equations. Is that okay? The same. So I say V final is V initial plus AT. Remember? Now it will be omega final is omega initial plus alpha t. The only thing that doesn't change is time. Time is the only thing that is common that doesn't have angular counterpart. But every other thing changes. So A changes to alpha. V final changes to omega final. V initial changes to omega initial. And T remains T. So we say starting from rest, a car accelerates at 2 meters per second square. And I say if the final velocity is this, find the acceleration of the car. I will give you the same problem for circular motion. Starting from rest, a fan rotates from an angular velocity of 0 and it reaches an angular velocity of this with an angular acceleration of this. Find the time. The same. So the same problem we have for linear motion, we can convert to angular motion. But the beautiful part about angular motion is you can always go from linear quantities. You can get V final. You can get V initial. You can get A from A equals R alpha, V equals R omega, and S equals R theta. You can always run around from this. Is that okay? You can always run around from this. Now the second equation is V final square is V initial square plus 2A X final minus X initial. The same. I'll do it here. Omega final square is omega initial square. Is that okay? Plus 2 alpha theta final minus theta initial. So theta represents my x now. So from linear displacement, I represent angular displacement. Okay? And the same, we have that x final minus x initial is v initial t plus half at square. So the angular equation becomes theta final minus theta initial is omega initial t plus half alpha t square. You see everything now? The same. I say x final minus x initial is v final plus v initial divided by 2 bracket t. The same thing here. Theta final minus theta initial is omega final plus omega initial over 2 bracket t. The same kinematic equations. You solve the same problems the way you solve problems in the linear case. Is that okay? The same thing. The same thing. Okay. So now we've seen several things. We talked about centripetal force, the acceleration, this. Now let's go to some applications, okay? Applications. So the first application I would like to introduce to you is a body moving in a horizontal circle. Just simple case. Is that okay? Simple case. Simple case. Very simple case. So it's like this. You're moving in a horizontal circle like this. So somebody is holding this guy here. This guy is holding it here. And it's going in a horizontal circle above his head. So this is the radius r. So you just have that the tension in this circle is just the centripetal force, mv squared over r. That's all. The tension is what produces this, the centripetal acceleration or the centripetal force. Is that okay? So that's all you need for horizontal circle. So that's case 1. Horizontal circle. So this is an approximation when you are moving at a high speed. You know when you move slowly, the circle will fall down. If you move very fast, that's when it stays flat. If you move slowly, you get what we call a conical pendulum. It will go in a circle with some angle like this, theta. It will go around the circle like this if you move slowly. Or if you move very fast, it becomes a purely horizontal circle like that. Is that okay? Now, the case 2 is this conical pendulum. How do we solve the conical pendulum case? For conical pendulum, the mass has mg weight going down. That's the mass going in this circle. Is that okay? Centripetal force goes this way. Is that okay? And the tension in the string T is what furnishes the centripetal force. But the tension in the string is up here. This is the string up here. This is a cord or a rope holding it. Now, how do I relate this guy to this guy? That's the problem now. Is that okay? So depending on the angle I'm giving, so I might be giving this angle. Sometimes they might give you the angle to the roof. You just work with whatever angle you are given. If this is theta, this is also theta, then I can do t cosine theta is mg. And t sine theta is the horizontal component. That is my centripetal force. T sine theta equals mv squared over r. Then I'm done. Is that okay? I'm done. So I can divide both sides. So t sine theta over t cosine theta is mv squared over r divided by mg. So when I do that, t cancels t, sine theta over cosine theta is tan theta, is just v squared over rg, where theta is the angle inside the conical pendulum. If the angle was the angle outside, I'll get a different answer here. Is that okay? So beware of the angle. So from here, I can get the speed of whatever is going in the conical pendulum. And when I get the speed, I can put it here. I get the tension in the string. Is that okay? We're going to solve examples on this. But now I'm just giving a general indication of what's going on. Okay? Good. That's for a conical pendulum. Now let's look at the case of okay, let me have you try this problem. Okay, I want you to find the tension and the speed of this circle. So this is 1.5 meters long. The mass is 0.25 kilograms. Is that okay? And the angle here is 30 degrees. Is that okay? I want you to find the tension in the rope T and the velocity V. I want you to do it up here. Yeah, come try and do it up here.
Okay. Get out. Oh, sorry. All right. So I did have a quick question here.
Yes.
So, since I have this angle here, could I make this a 90-degree angle?
Of course. Then that will
fill
be
this
60.
into
Exactly.
60?
Exactly. And then you can use what I have got in here.
So then, that means that this angle is also 60 degrees.
Exactly.
And then
Sweet.
this one would be 30, which we don't really care about right now. So we have a mass pulling down of 0.25 kilograms. We have to find T and find V. So finding T, we're going to do T cosine 60, right? Sine 60, and T sine 60 as well.
Yeah. So T cosine 60 is what? So where is cosine 60? What component is T cosine 60?
Give me 1 second. So, can you repeat the question one more time?
Yeah, so T cosine 60 is either horizontal or vertical. T sine 60 is either horizontal or vertical.
It's the horizontal.
No, vertical. You're pointing vertical, but I said horizontal.
Vertical, excuse me.
So the thing is, the way to know it is, in my vector class, I explained, if you know the angle, instead of you drawing this opposite hypotenuse, the axis that has the angle is always cosine to that axis and sine to the other one. So since the vertical has the angle, it will be cosine 60 for the vertical and sine 60. That's the trickish way to.
Okay. Okay.
So it's not always cosine and sine. If I wanted to use 30, which is this one, it will be cosine 30 for the horizontal and sine 30 for the vertical.
Okay. So T cosine 60.
So what else is in the vertical now? So T, don't forget, is going like this. It's holding it up. So if I do T cosine 60, I'm doing this. That's the vertical component. So what is in this mass that is also vertical?
The weight.
Exactly. So that is what will be the
okay, so 0.25 kilograms.
Times G. That's the mass. So times G.
Times G.
Exactly.
So
that's the weight now.
Okay, so I put weight on this side.
Exactly.
Okay.
Yeah, you can use 10. That's okay. Is that okay? So weight is there. Okay, now T sine 60 will be what?
The same, wouldn't it?
No. You are looking at horizontal now. So what is acting horizontally? So horizontal is here.
Right.
So t sine 60 is going in this direction, t. So what will this cause? That is the one that.
Oh, the centripetal force.
Exactly. Now you're communicating.
See, and I'm trying to remember. So I remember the centripetal force.
It's just here. It's mv squared over r. Exactly. Just need that. It's a long derivation. I might derive it in our next class.
So r.
Just takes a while. Yeah.
R is 1.5.
So you don't need all that. You can just now divide both equations like I did. So you know that tan theta is v squared over rg. So from here you can get v, okay? When you divide both equations. So tan theta
60
exactly
equals v squared
over rg. So you know your r to be 1.5.
Mm-hmm.
So from there you can get your velocity. Is that okay?
Yep. So 1.5 times 10. And right now I'm solving for velocity.
Exactly.
Oh, okay, I see.
Is that okay?
Yes.
Mm-hmm.
So 1.5 times 10, that comes up to 15, right?
Okay.
So 15, multiply both sides.
Exactly. And then take a square root, and then you're done. Is that okay?
Tangent of 60.
Yeah, I think that should be either root 3 or 1, but I think it's root 3.
3?
Yeah.
Okay, we'll go with 3.
Let's see. Cosine 60 is half, 1 over 2. Sine 60 is root 3 over 2. So tan 60 is opposite over, yeah, root 3.
3?
Yeah.
Square root of 45 is...
No, square root of 3. Tan 60 is square root of 3. So
yes.
this is 15 times square root of 3.
Oh, the square root of 3.
So
oh,
I see. Squared.
I see.
So v becomes the square root of 15 times the square root of 3.
Oh, okay,
square
I see.
root of that. Is that okay?
Yes.
So if you like, you can square both sides first to remove the square root, but it's up to you. But you can just use your calculator to finish that out. Yeah. So I just want you to understand, you cannot put it back in any of these equations. So like this one directly can even give you t, because you have the mg, so you can get your t directly from that one.
And that's what I was
cosine 60 is half.
thinking of.
So cosine 60 is half.
That would be the vertical component,
exactly.
And then you would just add them.
So half. Yeah, for this one, you don't even need to add, because when we divided these equations, we eliminated t. That was how we got the velocity to come in separately. But this one gives us t, only this one. So t cosine 60 is t times 0.5 equals 0.25 times 10. I'm done, I get t. So t is just 0.25 times 10 is 2.5 over 0.5. Which is what? 1.25. So I'm done, that's all.
So that's t, is that just the vertical component?
No, that's t, that's the whole t, yeah.
Okay.
So t cos 60 as a whole, that's the vertical component of t. T sine 60 as a whole, that's the horizontal component of t. But t itself you can get from here.
Okay.
So that's the original thing that was acting here.
Okay, and since we have this side already acting, that's...
Since we can get the vertical component equation, we can find t from that vertical component equation.
Okay.
Is that okay?
Yep. So then
we just got v from here.
And then we got v from there. Okay.
Is that okay?
Yep.
Okay, so let me go to the next problem. Okay. Thank you.
Thank you.
Alrighty. So we've seen the horizontal case. We've seen when the velocity of the horizontal is not enough, you get a conical pendulum like this. And we've seen how to solve this. Now let's look at a vertical circle. So I whirl a circle around in a vertical circle. I think I'll need that thing right now, your circle that you said you have. It might be helpful right now to describe what a horizontal circle is, a conical pendulum, and a vertical circle, so the students will understand what's going on. You wipe the board while you are bringing that out.
So as long as you don't flip it around, it should be good.
Oh yeah, that's good. That's a good one. Show it to the camera. Good. So can you give me an example of a vertical circle?
Mm-hmm. So vertical.
No, that's horizontal. No, that's vertical now. So this is a vertical circle. Mm-hmm. Good. Now, a horizontal circle will be the same thing, but above your head. Then a conical pendulum will be something like this.
So it's got a long rope.
You see? The circle is not perfect, but I'm trying. So this is a conical pendulum. You see that?
Mm-hmm.
So it's not vertical, it's just in between. That's the case we did. And then if I do horizontal circle, it would be something like this. You see that? If I spin it hard enough, it stays horizontal. And then vertical you just did. So now I want to do the vertical case. See what happens in the vertical case, okay? And I want you to understand there are two types of vertical cases. And one is the one with the rope, which I will explain. And then there's another one that is not with a rope. That one is the one with like a Ferris wheel. Okay? So let me start with the one with a rope. So I have a vertical circle. Say I'm carrying a bucket right here. I'm hanging the bucket here on the rope. And I wheel the bucket around. Is that okay? Is that okay? Okay. So this bucket is going in a vertical circle. So I want to know what happens to this bucket at this point A, point B, point C, and point D. So this A, B, C, D. So this is the top of the vertical circle. This is the bottom of the vertical circle. And this is the midpoint. So B and C are the same scenarios actually, okay? Okay. I'll start from the top. At the top, you discover that the tension is pulling this down. Is that okay? Is that okay? And then you discover that the weight is also going down.
This bucket is on a string.
Yes. So the string is going round and round like this. So the bucket is always connected at every point, going around a vertical circle. So the string. So this is the bucket on string case. Is that okay? Or I say mass on string case. Is that okay? Yep. So at the top, what do I have? At top, point A, I have that the tension is mv squared over r. Is that okay? But the tension and mv squared over r, the tension is not the only thing providing the centripetal force. The weight is also adding to it. So the tension plus the weight is mv squared over r at the top. Is that okay? Then, here, again, if it's moving fast enough, so it's perfectly a vertical circle, the weight is going down like this. The tension is going like this. So they are different. The weight is a vertical force. The tension is a horizontal force. They have no connection at all. So at B, which is the same as C, the tension is just the centripetal force because the weight does nothing. The weight is vertical, the tension is horizontal, so they don't interfere. Is that okay? Okay. Then at the bottom, D, that is where you feel the most force because you don't only balance the weight at the bottom, you also lift up to accelerate. But at the top, you feel the less force. Is that okay? And you're going to see at the top, I'm going to show you from here, the tension is mv squared over r minus mg, right? Now let's look at the bottom. At the bottom, the weight is going down, your tension is going up, and your centripetal force is going this way. So your tension minus your weight is your centripetal force, mv squared over r. Your tension minus your weight is what furnishes the centripetal force in this case. Is that okay? At the bottom. So what is the tension here at the bottom? Becomes mg or mv squared over r plus mg. Now, which tension is bigger, at the bottom or at the top?
The tension at the bottom.
Exactly.
Because you add the weight.
Exactly. So that's what tells you need more force. That's where you feel the more weight as you go along like that. So this is just the case. Understanding how to solve this, you can be asked differently. Find the speed at the bottom. So this is speed at the top. I call VT. This is speed at the bottom. I call VB. So you can be asked this is the speed at the side. I call VS. You know. So when they say find the speed at the side, find the speed at the top, find the speed at the bottom, or find the tension at the side. So this tension at the top, tension at the bottom, tension at the side. Is that okay? You can be asked all these questions. So you understand the scenario and you know how to work it out. Yes.
So at the sides, you don't really need to calculate.
The weight does nothing to
the
that.
weight.
Yeah, the weight. Yeah, the weight is actually is not balanced at that point because the weight is still going to accelerate this thing down. Is that okay? But what we are concerned about at this point is the centripetal force, and that's the only thing the tension does.
That's just for the tension?
Yes.
Okay.
Are we good?
Yep.
So the second scenario is a Ferris wheel where we have people going around the circle. So you are seated on a chair here, and you are going round and around the circle. So there is no rope holding you. You are just going. So what you have here actually is a normal reaction, a normal force, Fn. And then you still have your gravity, Fg. Is that okay? So in this case, just like we did there, it is your normal reaction plus gravity, that is mv squared over r at the top, for top. And then at the bottom, you have your weight, you have your normal reaction, Fn, Fg. You don't have a tension in this case. So it is your Fn minus mg, that is mv squared over r in this case. Is that okay? So your normal reaction in this case is just like your tension of the previous case. Is that okay? But the only difference between these is sometimes you can be asked to find, say, the minimum speed at the top. So the minimum speed at the top is that speed when the normal reaction is 0. So it means you don't feel any support at that point, no support at all. You just feel relaxed. So you take this to be 0, and then you get the minimum speed. But sometimes you can have a normal reaction there.
So the normal reaction is the normal force?
Yes, the normal force.
Okay, why is the normal force at the top pulling down?
Yeah, because you are resting. So because of the centrifugal force, they call it, the one that tends to pull you out. You know, when you're in a chair rolling, you feel as if you are the seat is holding you, like you have pulled you into it. Yeah. So that thing holding you back there, that's your normal force that's pushing you back. So the normal force is pushing you back towards it. You see here, it's also pushing you back towards here. Is that okay at that point? Yeah. So we're going to solve examples on these different cases. But I just want you to understand how the tension, and sometimes you can use that for the tension. They might tell you, find a minimum speed at this point also. That is when the tension is 0. Is that okay for the minimum speed? It means the tension here has to be 0. Yeah. So we're going to solve examples here, actually. And then things will become clearer when we start working examples. Okay. I just want to go straight to 2 more cases. Okay. That is the cases of banking on the road. So the angle, when you see some road, you see they are banked at some angle for cars to stay on them like this. So you have a car like this. You see the road is at some angle like that. Is that okay? So this is called banking angle. Is that okay? So that is the physics of the banking angle, and I want to explain that also, how it works, the physics of the banking angle. And then after I explain the physics of the banking angle and how it works, we are going to do examples on this to see how to solve the problems. Okay? So here,
how much time did you have on your camera?
Oh, I think we should have some more time. Yeah, we still have like an hour. Well, I'll be done in like 30 minutes tops. Yeah, 30 minutes. So it means we've gone like 45 minutes already. You know, it had an hour 45. So
just double check.
Yeah. So if I have a car at some banked angle like this, is that okay? So we're going to do some different physics now. So the weight is here, mg. If here is theta, I draw a line like this here. Here is also theta, right?
Normal force.
No. But the problem is, I know there is a centripetal force here that holds this guy to the center. Is that okay at that point? And my normal force is always going up here, F normal. Is that okay? Sorry, my normal force is here for the inclined plane. Is that okay? Now the point is, this normal force is what is going to have 2 components now. So if here is theta, it means here is also theta. Is that okay? So normal force sine theta is what gives us my centripetal force, mv squared over r.
Now, are we looking at the back of the car as it's going on?
No. Yeah, the back is going on the road.
Like
so this, yeah, exactly. So this can be like a turn or a roundabout or something. So the car
is not going up a hill. It's
no, it's turning. So going up a hill will be going this way. So the car is going in this direction like that.
Okay, that makes sense.
Is that okay? Yeah. Now, the normal force sine theta is my centripetal force towards the center, and the normal force cosine theta balances my weight, is my mg. So these are the two equations I want. And this is the no friction case. In fact, that is the aim of banking roads. So you can move and you don't need friction to hold you. So the angle keeps you so you don't skid off the road, no matter how fast you're going. But sometimes there's some speed you skid off. So we're going to come to those two cases. Now, if there is no friction, so this banking angle holds you like this. So I can divide these two equations. Say this equation 2, this equation 1. So I say equation 2 divided by equation 1. So it means Fn, or say equation 1 divided by equation 2, sorry. So it's Fn sine theta divided by Fn cosine theta equals mv squared over r divided by mg. Is that okay? I get the same thing. Sine over cosine tan theta equals v squared over rg. The same thing I got from the conical pendulum problem. Is that okay? But you be careful with the angle there. Okay, yeah. So where theta is the banking angle. So I can say, find the angle of banking of a road if I want a car to be able to speed at this speed. So you just put the speed, you get the angle when there is no friction. Is that okay? Okay, now if there is friction, the story is going to change. In the presence of friction, so two things can happen. In the presence of friction, if you move too slow, you start sliding down. If you move too fast, you skid off. So there is a range of speed, a minimum speed where below which you slide down, a maximum speed above which you skid off. Is that okay? So normally we want to get those two extremes, the minimum and the maximum. Any speed in between those, you are fine. But at that minimum, you are on the verge of falling, and that maximum, you are on the verge of skidding off. Is that okay? So how do we solve that problem when we have friction? So in the presence of friction, I still have my car like this. Now let's find the maximum friction. So I'm trying to skid off. So my friction is going down. Is that okay? So I'm trying to.
Why does friction pull you down?
Because I'm trying to skid off. So I'm trying to find the maximum speed. So my car is trying to skid off. Is that okay? If I'm trying to find a minimum speed, I'll draw friction the other way because my car is trying to slide down. Is that okay now? So this is for maximum speed. I want to find the maximum speed and with friction. Is that okay? Without friction, you only have just one particular speed you can go. Is that okay? One good speed you can go without friction. Is that okay? Okay. Now, with friction, I still have my normal force like this. Is that okay?
Yep.
I still have my centripetal force in this direction. Note, the centripetal force, I don't write it here as centripetal force. It is this component that equals centripetal force. It is not a force you can put on a problem by itself, like a normal force or weight. It's a consequence of a force. Is that okay? It's a consequence of a cause. So here, I have my weight down mg. Okay? So now I solve my problem now. So now solving my problem, I know this is theta. I know this is also theta. This is also theta. Is that okay? Now two things are going to come here. This is theta. This is also theta. Is that okay? The z. Is that okay?
Yeah.
So friction cosine theta plus normal force sine theta are the two things contributing to centripetal force in this case, mv squared over r. Are you seeing that? And then normal force cosine theta equals mg, but I also have friction sine theta coming down plus friction sine theta. Is that okay now?
Yeah.
So those are the two things that I have. So now I'll solve for mass here. Mass here is normal force Is that okay? Cosine theta minus friction sine theta all over G. That is my mass, right?
Yep.
I take this mass, so I'll call this equation 1. I call this equation 2. I call this equation 3. I take this mass, equation 3, which I got from equation 2. I put it in equation 1. Is that okay? So if I do that, if I put 3 in 1, what do I get? I get friction cosine theta plus normal force sine theta equals, instead of my mass, I have v squared over r multiplying my mass. My mass is normal force cosine theta minus friction sine theta divided by g. Is that okay? Mm-hmm. Good. But I know that frictional force is coefficient of friction times normal force. So I put this here. So my frictional force becomes normal force times coefficient of friction cosine theta plus normal force sine theta. I'm just substituting for friction equals v squared over rg times normal force cosine theta minus, instead of frictional force, I have mu normal force sine theta. Is that okay?
That way you get rid of the variable of
normal force. That's the only thing I can get rid of right now. Is that okay? That's the thing I can get rid of right now. Now, let me give more space here to continue. At this point, I have mu cosine theta plus sine theta equals v squared over rg into cosine theta minus mu sine theta. That's all I have for right now. Now, rg comes here. Is that okay? And cosine theta over that comes here. So I have v squared equals mu cosine theta plus sine theta divided by, so I have rg multiplying here. Is that okay?
Oh yeah.
Divided by cosine theta minus mu. Are we good? Let's make sure I didn't miss anything here. So this is mg. So m is this minus that divided by g. I put that there. V squared over rg. Okay, yeah. So this is it. Rg times that. So this is the maximum speed. So if I take square root of that, I get what I want. Is that okay? If I want to get the minimum speed, I change the direction of the friction to that side. I solve everything. I'll get the exact same thing with the signs changed. Minus up, plus down. Is that okay? I can leave that as an exercise for you to try. But the thing is, we can be asked problems regarding this. And when we do all the examples we're going to do, this is just explaining in my next class. We're going to do examples from the beginning to this point and solve a lot of problems as we go along. Okay? I also have another separate video I added to the playlist on this. It was a recitation video I taught just the student working on this problem for like 30 minutes. It's just on this thing. You can watch that too after watching this to get more. Okay? Okay. So I'm going to stop here for today. Then we already spent more than an hour. Then we should be good. So we're going to take more examples and see how to solve these problems the very next time. And then I will introduce you to drag. Yeah, I think that's the last thing. So let me explain that briefly here. The concept of drag force. So you know, when we fall under gravity, you fall with G, right?
Yes.
So when you fall, when there is air resistance, you are falling down, and there is air resistance, you experience what we call drag. Is that okay?
Yes.
So that drag is half rho C A V squared. Is your drag force. So this is the coefficient of drag, coefficient. Depends on the surface. And this area, this density, this speed. And then you keep falling through that. So maybe it could be liquid. You throw a stone in a liquid. It keeps falling and then it just stays falling steadily. So it's falling with what we call the terminal speed at that point. So that terminal velocity is the point where the drag force, the force of drag, which I call this, equals the weight. So when this guy equals mg, that's when this guy becomes the terminal speed. So from here you can calculate terminal speed when you equate these two together.
So once you reach terminal velocity,
you have equilibrium.
Accelerating.
Yes, you have equilibrium. Yeah. So your weight balances your drag force, basically. And then we can use this to solve problems again. Okay, so this is your cross-section area facing the drag. This is your speed. This is your drag coefficient, and this is your density of the medium. The density of the medium, the air, or whatever you're going through. Okay, and this is your mass, and then we can solve for that.
Which is why you fall slower in water
exactly.
than air.
Exactly. So terminal velocity here will be, in this case, 2mg divided by rho Ca squared. Because when I equate them, I make V Soviet formula like that. Okay. Yeah. So we're going to solve examples on these also. This is just the last thing for this. Yeah. So thank you, and then I'll see you next class. Okay. Have a good one.
Thank you. You too.
Time to stop this. Stoppy.